for a nice introduction. I'm Rıza. I'm a PhD student in Eindhoven. I have just traveled from Netherlands, and I'm still trying to adjust the altitude change because Eindhoven is like, it has an altitude of 1 meter, literally, and here it's, on a different scale, literally. So today I will talk about our latest work on chemical language modeling, which is using structured state spaces. But before diving deeper into what we do and how we do it, let me motivate you. Why do we need such models? And the answer is really hidden in the vastness of the chemical space. Chemical space, as we define it, it's the set of possible drug-like molecules, and it's estimated to contain 10 to the power of 60 compounds. This is a huge number, of course. We cannot just go to the lab and test every single possible molecules, and that's why we need some computational methods to navigate our search in this huge space and to highlight some promising molecules for us. One technique that has been very useful in the last decade and was validated in the lab is called chemical language modeling. And here is a typical pipeline on how to get a chemical language model. You first start with a generic set of molecules, very typically Campbell, just some molecules tested in some bioactivity assays. And then you throw a sequence model on top of this data. Here, a sequence model, it's a type of generative deep learning model, and it's characterized by being able to process sequence inputs and then giving, again, sequences as output. So it's a sequence-to-sequence mapping. And then once you have such a model, then you can start generating molecules with this model, and then you have a de novo design pipeline that just works. So here, in this fashion, in this chemical language modeling idea, what you put in here is very important, because the sequence model is responsible for learning the properties of the fed-in molecules, and then mimicking those properties or enhancing those properties by its designs. So what you put here is very, very essential and has been an active research field, of course, in the last decade. The most two popular approach are LSTMs and GPTs, like the usual suspects, and they both come with respective weaknesses and strengths. LSTMs, as we know, they process input from left to right, one-to-one, and at each step they compress information into a single vector. So they're actually trained to be efficient in memorizing the history. And this means that they're also very efficient to then design molecules because, again, they can do everything one-to-one from left to right very fast. But since they have this compression built into them, they might actually struggle compressing some information into this latent representation and, then have some struggles. GPTs, on the other hand, they have the exact opposite idea. They let information flow from everywhere, so they have a holistic look at the input, so they can actually capture global properties better than LSTMs. But then when it comes to generation, they don't have this stepwise structure built into them, and then you need to do some tricks, some additional tricks to actually make them more efficient during generation time. And of course, when you have such trade-off in your hand, of course you ask the question, what if we can get the best of two worlds? And here is such an approach that might actually combine those properties. It's called Structured State Space Sequence Model, or SFORT in short. It was proposed 1.5 years ago, and they're often characterized by those state space equations. A state space equation, it's actually two equations that, again, takes a sequence element as input, UK, in the equation, and then gives an output, sequence output as the, and that gives a sequence output. In between, it computes a hidden state, very similar to LSTMs, and then has this stepwise structure. So if you plot a state space equation, again, you have the inputs at the bottom, outputs at the top. It's a sequence model again, and it processes the sequence one by one, very similar to LSTMs, and has a very similar computation graph. But what is also very cool about those state space models is they can be immediately reformulated with the same set of parameters, ABC in this case, to be a convolution, to be a global convolution. And global convolution means that now you have an input, And then you can process this input all at once by looking at all the tokens, all the input elements globally. So in this sense, they're actually more similar to GPTs because they have access to everything at the same time. And they're also very fast to compute because convolutions, computational people, we just love them. They're just super fast and efficient. And so it means that in general, when we have an S4 model or when we have a state space model, we have this dual formulation. We have this convolutional structure which might help us actually learning some global properties better. And then we can actually go back to this stepwise recurrent structure to efficiently generate new molecules and explore the chemical space better. And of course, this idea, we didn't propose this, it was proposed in 2022, and it was tested for generating text, images, and audio, and it has worked remarkably well in those domains. But now the question arises, what about molecules? Can we use this S4 model to generate molecules? Here, we seek an answer to this question. So we, again, use this typical chemical language pipeline. We start with a set of generic molecules from Campbell, 1.9 million. And then this time we put an S4 on top of those molecules, and then we generate. And of course, then we start asking questions. First, can S4 really design molecules? Can it be a molecule generator? Yeah, so we measure three usual suspects of our field: validity, uniqueness, and novelty. Validity is the fraction of designs that actually correspond to a molecule. So yeah, can this model generate actual molecules, or is it just random strings that it generates? And then uniqueness is the fraction of unique molecule it generates. So is it any redundant in terms of generation? And then novelty is the fraction of molecules that are not in the training set, just to check if the model is basically fetching stuff from its training set, or in other words, just cheating. Those three metrics, they're very commonly used in the literature, but we also know that they can easily be cheated by even trivial benchmarks. So here, even though we see that S4 is outperforming LSTM and GPT, I would definitely not overinterpret these results. This is more like a sanity check, just to show that S4 can indeed learn how to generate molecules. And these are, again, just any molecule. But what we are more interested in general in drug discovery is to generate molecules with some properties. And yeah, and again, in general, as like a first step, generating molecules with bioactivity with some binding towards a protein target. Here we curate 5 different sets of binders to 5 proteins from the lit-PCBA data set. Here I will discuss the results only for the first 4, just for brevity. The results for TP53, it's available in the preprint. And then once we have those binders to those proteins, we further train S4 with those binding molecules. And then again, we ask questions. First question we ask is whether S4 can separate actives and inactives. Here the motivation is, in the end, we want to generate bioactive molecules, active molecules using S4, but as like a first question, can this model even appreciate what makes bioactivity? Does it have an idea of what is an active, what is an inactive molecule? To quantify that, we feed some held-out test set molecules to S4, and of course to other chemical language models in our study. And then we ask S4 to score those molecules using the log likelihood of those sequences. And then using those scores, we rank the molecules. Here, a good model should rank the active molecules at top and the inactive molecules at the bottom. So, and then of course we quantify the performance in this ranking across proteins. Here you see the results for S4, LSTM, and GPT, but I bet you don't see it because projection is failing for the service quality that it promises. But what we see here on the x-axis, we measure the performance in different selection sizes, 10, 50, and 100. So top 10 of the list, top 50 of the list, and top 100 of the list. And then on the y-axis, we actually measure how much of the test set actives is placed in those lists. What we see almost across the board, with just one exception as far as I remember, is S4 is actually outperforming GPT and LSTM in terms of capturing what is relevant to make bioactivity for that specific protein. What we also see is the last bar on each subplot, GPT, it's also outperforming LSTM, and this gives us actually like a suspicion that indeed this global look at input rather than one-by-one processing can actually be more beneficial to capture properties of those chemical spaces and of those molecules. Okay, and of course, in the end, we want to design, not just rank actives and inactives. And to test S4's capabilities on that, we design a prospective study. We fix a protein, MAPK1, and then we create binders to this protein from Campbell. We again fine-tune S4, using those strong binders, and then design and rank, and of course, evaluate, this time using molecular dynamic simulations. So we get, top 10 designs from our model. So here, the molecules that you see from 1 to 10 are designed molecules, they're de novo designed. And molecules that you see from 11 to 16, they are nearest training actives to those designs. So we also keep them as like a sanity check. And then we run extensive molecular dynamic simulations on those designs. And we compute delta G of the protein ligand, of this interaction. We see that, and in general, in case you're unfamiliar with delta G is a lower better metric. So the lower the score, the better the interaction. And in general, they say that if it's below -9, then there is actually a strong possibility that it would be a binder. So in 8 out of 10 designs, we see that the delta G is actually below -9. Which gives us a very strong indication that S4 can actually design strong binders for MAPK1 protein. We also measure the delta G of the known actives as like a sanity check just to see whether our MD simulations are running properly. And we see that, yes, they all get delta G values below -9, suggesting that what we are doing is indeed believable. We also report Ki values just as just to give you a reference of the strength of the binding. Okay, and then, S4, it really comes across as a positive model to us, but no model is state-of-the-art or no model is good in just one study. So we definitely encourage everyone to work more on S4, and to encourage that further, we just released the open source Python repository that hopefully anyone can use as easily as possible. In just 4 lines of code, you can create your model, pre-train and fine-tune, and then just design molecules. If you use it, please let us know what you think of it and how S4 performed in your task. Meanwhile, of course, we have more questions than ever now, because that's just the research. And now we are still running more experiments on S4, and we want to go to the wet lab. We want to get some wet lab validation using S4. And of course, one of the most exciting ideas is to apply S4 to different molecule types, like polymers or proteins, which are again super relevant in drug discovery and chemistry in general. The best slide for me is to share the credit with all the amazing people I have done this work with. Yeah, Francesca was the supervisor. She's the supervisor of our group, and Sarah was the bachelor student who has started this project actually as a bachelor thesis. And Emanuele, he's a postdoc in our group who has run the molecular dynamics simulations. I thank them all, of course. And I thank you for sparing your time. Here is the link to our preprint and code base. And here is my email address. If you want to reach just to talk or have a collaboration or whatsoever with S4 or anything else, just shoot me an email. Thanks.